Now let us quickly see some application. Depending on the time, let us see some actual circuits and also how some of these parameters improve. Now one of the most important thing to remember about negative feedback is, by applying negative feedback, your ordinary amplifier or the basic amplifier goes from its non-ideal situation towards the ideal situation. Now we know that when you talk about a voltage amplifier, what are the ideal conditions as far as the input resistance and the output resistance is concerned? I know that in a voltage amplifier, ideally my input resistance should be infinite. My output resistance should be ideally 0. Now we know that we can never get that with a voltage amplifier, but by applying negative feedback, we can go from the non-ideal stage towards the ideal stage. We may not reach there, but we would reach very close to it. Now how is it done? We will not, time does not permit us to do the derivation, but what will happen is, the way it is, how you would analyze it shown here. Now you could also intuitively say that since now the input voltage is getting reduced here, effectively the current gets reduced, therefore that is equivalent to the input resistance increasing. So that is a intuitive way of looking at it. So we see that by applying feedback, what I have done is, I have essentially reduced the current flowing, because I have essentially reduced the Vi here. So by reducing Vi, effectively I have increased my input resistance. So this is, so we are going from the non-ideal state to ideal. So if your input resistance without feedback was Ri, after applying negative feedback, your input resistance would become Ri times 1 plus A beta. That would be a substantial increase. If you plug in numbers, especially in an op amp, we know that A is 2 into 10 to the power 5. Now if you take a beta of typically, let us say 1/10, you would get A beta of 10 power 4 approximately. So you are going to jack up the input resistance by a factor of 10 power 4. Huge increase, tremendous increase. So this is why we said, by applying negative feedback, we are taking the amplifier from its almost non-ideal state towards the ideal state. What is the other advantage we get here? Now again, the derivation we will skip because of lack of time, but the way you do the derivation shown here, what you do is, to measure the output resistance, we connect a source. In our analysis, we would should never do this in an actual amplifier, but in analysis this is the way we do it. You connect a source, fictitious source, say Vx, and if you name the current Ix in this scenario, now when we measure, if you remember what we wrote in our expressions when we talked about common emitter amplifier, for measuring output resistance, the input side should be shorted. So you short circuit the input there. Now you find the current here, you would find that when you derive, you would find that the output resistance R0, which is here, reduces by 1 plus A beta, which means if it was R0 earlier, now it is R0 divided by 1 plus A beta. That is an extremely significant decrease. Now take the example of an op amp. If you plug in the numbers, you would be surprised. 741 op amp, the input resistance without feedback, open loop input feedback, input resistance is approximately 1 mega. The output resistance of the open loop 741 is 75 ohms, very high. But if you use it in the non-inverting amplifier mode, if you use it as a non-inverting amplifier and you substitute these numbers 1 plus A beta, we will just see quickly how you calculate beta. Now if you substitute it, you would see that these numbers drastically change, that depending on the beta you have there, the input resistance can jump from 1 megohm to maybe, let us say, at least theoretically 100 megohm. You may not get that, because 100 megohm, getting 100 megohm in a circuit is very difficult because of leakage resistance, your PCB. You can never get that in a microboard because of the leakage currents, but at least theoretically you have a possibility. Therefore you would see that very high in a very precision application. This is why amplifiers are soldered and printed circuit boards are made to avoid leakage currents. Now, so we see that in a voltage amplifier, the input resistance increases by 1 plus A beta, the output resistance decreases by 1 plus A beta. Now, another way of arguing is, we can say that whenever we have a series connection at the input resistance goes up by 1 plus A beta. We know that we get a series connection only when we have a voltage there. So, whenever you have a series connection at the input resistance would go by 1 plus A beta. Whenever you have a shunt connection at the input resistance would go down by 1 plus A beta. So, the same thing you could apply to the output also. Now, let us quickly look at the other amplifiers also. Now, for the current amplifier, by applying feedback, this is the detailed diagram, the equivalent circuit. Now, as we said, we have a shunt connection here and we have a series sampling here. We know that in a current amplifier, in an ideal current amplifier, my input resistance here should be 0, and we know that in any current amplifier you can never get that number, but by giving negative feedback you can make that Ri very close to 0, or you could reduce it substantially, and you can see that how it happens here. You have a shunt connection, so therefore the previous Ri gets reduced by Ri by 1 plus A beta. So, you see that in a current amplifier, by applying negative feedback, you are able to reduce the input resistance by a factor of 1 plus A beta. Now, we know that again in a current amplifier, the output is a current, therefore ideally this R naught should be infinite, and again we know that we cannot get infinite resistance, but because of the series connection, we said whenever we have a series connection we get a multiplication. Now, in this case also, because of the series connection, the output resistance here gets multiplied. So, again it is going from its non-ideal state towards the ideal state. Now, let us quickly look at the other two. We have the trans conductance amplifier, where we have a voltage mixing here. So, therefore, immediately we can say the input resistance increases by 1 plus A beta. Now, since we have again a series connection here at the output resistance increases by 1 plus A beta, and we know that this is a trans conductance amplifier, which means your input is a voltage input, therefore ideally the input resistance should be infinite. So, by connecting this series connection we are going towards that direction. Similarly, the output is a current, and we know that ideally R naught should be infinite, and by connecting this negative feedback, what would happen is R naught would go towards that side, so it would increase drastically. So, the output resistance increases by 1 plus A beta and the input resistance increases by 1 plus A beta. Coming to the last one, we have the detailed diagram here, the trans resistance amplifier. Now, here we know that the input is a current and the output is a voltage, and as we said, ideally the input being a current, this Ri should have been 0. Now, by connecting a shunt connection here, we are going towards that. So, if the previous input resistance is Ri, the one with feedback would be Ri divided by 1 plus A beta. Similarly, the output side, we have a voltage here, and we are sampling a voltage, and we said whenever we do a shunt connection here, the output resistance go down, and this being a voltage here, we know the ideal situation, the R naught should be 0, so it would go towards that direction. We would get, so in summary, in a shunt amplifier, feedback amplifier, the input resistance decreases by 1 plus A beta, and the output resistance also decreases by 1 plus A beta. Now, what I will do is maybe another 10 minutes I will spend on the feedback topologies before going to the second topic, which is oscillators. Let us see some examples of what we studied. Okay, let us see a few examples. We have 4 topologies, so in each case I have chosen a ideal situation using op amp, and some of the circuits will be very familiar to you. some of them may not. Now in a very good example of series shunt feedback is the non-inverting amplifier, which we are very familiar with, and now we see what is beta. Now Vf is nothing but V0 by V0 times R1 by R1 plus R2. So we know that Vf is equal to beta times V0, therefore beta is nothing but R1 by R1 plus R2. So we said in the case of a series shunt feedback or voltage mixing, voltage sampling feedback, the input resistance increases, and intuitively we could see that here the connection, there is no other resistance connected to ground or anything here. So intuitively we can see that the voltage which is fed back will decrease this Vi, will try to reduce it. So effectively the current flowing into the amplifier gets reduced drastically, and because of the shunt connection here, the output resistance would decrease drastically, and that again would make it towards the ideal situation. So this is a circuit which is an example of series shunt feedback. So we could remember, at least this particular example we could remember, that a non-inverting amplifier is the case of a series shunt feedback, and that's an example of a voltage amplifier, therefore it is a series shunt feedback circuit. Now what we have here is another very familiar circuit again, another example of series shunt feedback, which is nothing but an emitter follower. So emitter follower is again an example where you see that because of the resistance here, unbypassed resistance here in the emitter, this is subtracted, and we said when we talked about biasing, we said that by putting a resistance, unbypassed resistance in the emitter, we said that any changes, especially we said that VB is very sensitive to temperature, but that change is countered by the resistance, unbypassed resistance put on the emitter. So we see this as a very good example of voltage sampling, voltage mixing or series shunt feedback, and we know that the input resistance will increase, and we know it very well from the example of an emitter follower, the input resistance is much higher, and again from the example of an emitter follower we know the output resistance is very small. So again a very good example, a discrete circuit example of series shunt feedback. Now let's look at the next topology. So let's see again two examples of shunt series feedback, or essentially the feedback for a current amplifier. So what we have is a op-amp based current amplifier. So you have the current source here, and you can see a certain amount of the current flowing into the op-amp, okay, and you have the feedback current here flowing into the output. So you can see whatever is Is here, Is minus If is what is flowing into the input, which is almost 0, and the current I naught is shown here. Now this being a current source, the current flowing through the load, in this case the load here is R1 here. Now in a current source, the same current should flow irrespective of whatever resistance you put here. So effectively by analysis we can see that the output resistance of this particular amplifier would be very high, so that the current irrespective of you would get the same current. Now let's look at the another discrete circuit example, a quick example of a shunt series feedback, which is a current amplifier. And you might remember when we talked about common emitter amplifier, I mentioned that a common base amplifier is a example of a current amplifier. So what we have is a conceptual diagram of a current amplifier. Now again the same thing, you have the way it's connected here is to show the way a feedback topology. Now you have the input current here, and you have the feedback current, this is the output current, and you have that feedback here, and you have the input current shown here. So this is conceptually a diagram. Now what I have here is an actual diagram which looks quite complex, but let's have a quick look at it. So what you essentially have here, two stages. You have a common emitter stage here and another common emitter stage here. The second common emitter stage, you have an unbypassed emitter resistance here, and this is a current amplifier. Therefore, what I need to do is I need to take a shunt connection. So you can see a shunt connection taken here, and you have a feedback resistor here, RF here, and output we need to sample current. So we know that approximately the current flowing there would be approximately rather a proportion of that would be flowing in the emitter here, and that is sampled here. Now what we have here is an equivalent circuit. Now I would upload this in Moodle, so you could look at these circuits leisurely, but one very important thing need to be kept. Now when we talk about feedback, you would see that when you use an op-amp, you would get almost close to ideal situation, but discrete amplifiers like the ones which you make with transistors are very often very difficult to analyze, and things may not be as straightforward as it is. Now the way you would identify is to look at the way a feedback is done. Like you need to figure out whether the voltage, the feedback at the input, is there a shunt connection, and again of the output side. So sometimes things may not be very straightforward, may be difficult to figure it out. Now this is an example of an op-amp based transconductance amplifier. Again you have a voltage as the input, a current as the output, and the voltage which is fed back here is Vf here, which is a fraction of the output current. Now we have another example of a transconductance amplifier using a discrete example. So this is nothing but the common emitter amplifier which we are familiar with, unbypassed. So the unbypassed common emitter amplifier is an example. You can think of that as an example of a transconductance amplifier with negative feedback, and we know the reason. Input side, you have a voltage here, so you have a series mixing here, because of which the input resistance increases, and the output is a current. And if you analyze a common emitter amplifier with unbypassed resistor, you would see that the output resistance increases. So this is why this is a series feedback. Now coming to the last one, again this is a circuit which you are very familiar with. This is the circuit of a inverting amplifier. So an inverting amplifier is a very good example of a shunt feedback. Now generally we don't appreciate this as an example of a trans resistance amplifier, but I assume that you would have definitely noticed something very interesting in an inverting amplifier. In an inverting amplifier, because of the negative feedback, because of the virtual ground property, these two terminals will be the same potential. So essentially, if you use this as a voltage amplifier, the input resistance is nothing but R1. So therefore, inverting amplifier is a very bad choice as a voltage amplifier. So if you need a voltage amplifier, you always need to use non-inverting amplifier. So strictly speaking, an inverting amplifier is essentially an example of a trans resistance amplifier, and the current which is flowing here, so you can think of the input as nothing but a current flowing here. And one thing very interesting here is we have the ideal situation, we have a short circuit. So this is beautiful. Op-amp gives you the ideal situation. So you have a short here, and we know because of virtual ground property this also will be a short here. So the entire current from the current source will flow here, and that entire current, assuming hardly any current flows into the op-amp, would develop across this. So the inverting amplifier is a very good example of a shunt feedback. Coming to a discrete BJT based amplifier, this is an example of a shunt feedback. So you can see that you have a connection from the collector to the base here, and again whenever you have a shunt connection at the input, we know that the input resistance decreases. And again, as I said, being a BJT amplifier, we should remember that it's not as ideal as it is in the op-amp case, so analysis also may be difficult. But again, at the output side also you have a shunt connection. Now this is a trans resistance amplifier, so input is a current, output is a voltage. So I hope you have now some appreciation of what negative feedback is and what the feedback topologies are. I have about roughly 15 minutes. Now what I will do is we will go through the second topic, which is on oscillators, and depending on the time we would again have a quick recap. Now the first topic which we talked about, negative feedback, is an extremely important topic, but unfortunately it's not well done in most of the books, and things could be quite confusing. So I hope you would have got some understanding, and the way to understand these concepts is to go over it again and again yourself by looking at the block diagram and trying to argue, and things would make sense. Now let's now look at the second topic. So far we were talking about negative feedback, and we said negative feedback, when we say feedback, generally we mean negative feedback. Now in a we want to talk about applications of positive feedback. Now positive feedback generally is thought to be something very undesirable. Yes, it is undesirable in an amplifier. In an amplifier, if you have positive feedback, you would have instability, and you will not get what you want. But positive feedback can be used carefully to our advantage. So what we have here is again a block schematic, again the same thing which we did at the beginning, the exactly similar block, except that the mixing which we are doing at the input, now it's a addition. The first case it was a subtraction, now it's an addition. That's the only difference, but just by doing that the circuit changes drastically. The previous case we had a negative feedback, now we have a positive feedback. I leave it to you to analyze this. It's extremely simple, just 3 equations just like we wrote there. First equation is x naught is equal to a times xi. Second equation is the parameter xf here is nothing but x naught times beta. The third equation is xi is equal to xs plus xf. So 3 equations from which you could write an expression for x naught by, this should be xs or xi, xs should be, then you would get this to be a by 1 minus a beta. Now look at this expression. The previous case the expression what we had was a by 1 plus a beta. Now it's very obvious that we see here that in this case, if for any reason the a beta happens to be unity, then we have a situation where the closed loop gain, if we use the same term as we used in the case of amplifiers, you get a situation of a closed loop gain being infinite. Now what do you mean by closed loop gain being infinite? Now you could argue it this way. In an amplifier you gave an input and you got an output, just amplified version. But when you generate a signal, let's say you want to generate a sine wave, you don't give anything. All that you are giving is a battery, and that battery or the power supply is used to bias the circuit. So actually as a signal you are not giving anything. So without giving any signal to the input, you are able to get something at the output. So that way conceptually or intuitively we could understand what you mean by the gain being infinity. Now in the previous case we used the word loop gain for a beta, the same thing here also. Now there is a very big difference between what we did for negative feedback and what we did here. Now in the context of positive feedback for generating, let's say, a sine wave, what we are interested in, we know that we are talking, when we talked about an amplifier, the negative feedback, the feedback network was entirely a resistive network. You might remember, so this is something very important to remember. In the case of a negative feedback, the feedback network in the context, I am talking in the context of an amplifier. Now in a negative feedback, the feedback network has to be resistive. So essentially you are not bringing any frequency dependent function there. So the beta, which you can think of as the transfer function of the beta network, is purely resistive and is real. Whereas when we talk about this application, here the feedback network is not resistive. In fact, it is frequency selective. You could think of this network as a filter. Now, this filter need to have an order of 2 or higher. At least it should be a second order filter. Again, you could think of say conceptually or intuitively, you could think of the working of an oscillation or oscillator like this. You could think of noise being present in the circuit, rather in the environment, and this frequency selective circuit, which is a filter, which would pick up only one frequency, and only for that particular frequency it will satisfy the condition A beta is equal to 1. Now, as I said, in this case A beta is not real, it has both, it's a complex term. So when you say A beta is equal to 1, you have two things. So let me write that. So the condition for oscillation we saw that is A beta is equal to 1, and we said here definitely beta, but we might assume say A to be real, but definitely beta. So let us say A beta is a complex term. So to satisfy this condition, what we are essentially saying is modulus of A beta is equal to 1 and angle or the phase of A beta is equal to 0 or say 2 pi or multiples of 2 pi. So this is the condition for oscillation. So if I can satisfy using a frequency selective network these two conditions, the condition is that the modulus of A beta must be equal to unity and the phase is equal to 0, essentially saying that. So what is the meaning of this? Essentially what we are saying is at the frequency of oscillation A beta must be real and it should be equal to unity. Now let us look at an actual circuit and see how do we satisfy. So before we see that, let us see how do we actually implement an oscillator. So the way an oscillator is implemented is this way. You would have an amplifier and what you would do is you would connect the amplifier, you would have a kind of back to back connection of an amplifier and a filter. So essentially what we would get is, so let me draw this and show you. So what we're talking about is we have an amplifier whose gain is A, and what we do is we would feed that into a network which let us say is a filter. So let us talk about this being a filter, and the output of the amplifier is fed to this filter and the output of this filter is then fed back to the amplifier. Now as I said, in any circuit we have noise present. Now the purpose, how do we initiate oscillation? Now the way it happens is you could think of the filter satisfying this condition A beta is equal to 1 only for one case, and that would be for a particular case. Let us see now an example and see how exactly it is done in actual practice. Now what we have is a very popular circuit which is a very popular sine wave oscillator, which you can easily rig it up in the lab and almost always it will work at the first instance. But let us see what condition we need to satisfy. So let's understand this. As I said, you could think of this as two blocks. One block, this first block here, if you remove this particular network here, if I assume as some input coming into this V plus here, you could think of this block as nothing but a non-inverting amplifier, and we know that a non-inverting amplifier, the word non-inverting itself means that there is no phase difference between input and output. So if I have a signal here xi here, my output will be amplified by A times xi without any phase change, and the way it's connected here, we have two resistors here, we will come to that in a minute, and then the output of the amplifier is fed back into a filter here. So essentially what we have is a network here, you have an amplifier and a filter connected say back to back. So the output of the amplifier connected to the filter, and that's all. If you just connect supply, when you switch on power, it oscillates. How does it oscillate? Now let's look at the filter characteristics to understand how it works. Now this is the same circuit. Now this is a popular second order filter, and this can be easily analyzed, and if you write the transfer function, if you write transfer function V0 by Vi, you would see that the transfer function would be real only at one frequency, and that frequency is 1 by RC. At omega is equal to 1 by RC, you would see that the V0 by Vi will be exactly 1/3. Okay. So if you plot it, you would see that if you plot the modulus of this, so you would see that this particular second order filter would give you maximum value at omega naught, where omega naught is equal to 1 by RC. So now what is the meaning of this 1/3 here? So we see that, now again going back to our circuit, we can see that this non-inverting amplifier, now we have two R1 here and an R1 here, therefore we know the gain of this non-inverting amplifier is 3. So let's leave this small resistance here for the time being. So I have an amplifier who has a gain of 3, and here is a network which has a maximum value of 1/3 exactly at a particular frequency. So in this case the condition A beta will be satisfied easily only at one frequency, and that is the frequency omega is equal to 1 by RC. At that frequency the whatever is input here will be attenuated by a factor of 3, or if input is Vi here, you will get exactly Vi by 3, and the amplifier will amplify it exactly by 3, and at the input again back here you got the same Vi. So if you look around the loop gain you see is unity, and that's the condition for to be satisfied. Repeating, let me repeat it once again. So if I start from here, if I break this here, apply a Vi here, and I know that at omega is equal to 1 by RC, my output of my filter will be 1/3 of Vi. Now I amplify that by a gain of 3, so I get back my Vi. So therefore if you connect them together, at least it should oscillate. In fact you can conduct this experiment in the lab, break that loop, and you exactly make it 1/3, and then just close it, and you will be amazed that will continue to oscillate. So this is how a Wien bridge oscillator works. Now let me come to this particular small resistor which we have put here. What we talked about was all ideal. We said that ideally the gain of this amplifier must be 3, but we know that we are using all passive devices, rather passive elements here, capacitors and resistors. Now these resistors and capacitors will have losses. Therefore if you have exactly 3, you will never get oscillation. Rather if you keep gain very high, you would see that the output will not be a sine wave, it will be a distorted sine wave. Now it is very interesting. So I would, if you have not done this experiment yourself, I would strongly urge you to do this experiment, and you will be thrilled like a child to see this experiment. Even today when I do this experiment, it thrills me to see some of the things which we talk about, how you can easily see it in the lab. What you should do is, this particular resistor here, don't make it 2R, maybe make it 1.5 R1, and put a potentiometer here, and you would see that as you increase the potentiometer, as soon as it satisfies the condition, you will see the sine wave slowly popping up, coming into oscillation. and if you just leave it there, you would see a sine wave just dancing. It might just collapse, it might continue, and if you increase it further, you would see at some stage it's being stabilizing. If you go further, it will get distorted. So this particular circuit is an extremely useful circuit. At the same time, it teaches you something very, very important, that this circuit cannot be used as a practical circuit, because you need to satisfy that condition exactly, which you can never do. We can't do it manually. So therefore, Wein bridge oscillator, when it is implemented, what they actually do, they would have a nonlinear amplitude control. Very often what is done is, you would put a Zener diode across the feedback path, and you would choose in such a way so that if by any chance the gain increases, the Zener path would decrease the resistance of the overall impedance there, and that will keep it in oscillation. So I have come to the end of my lecture. Let me spend another 2 minutes to quickly recap on what we have done. Now we talked about, let me maybe spend another minute on positive feedback, because I spent a lot of time on negative feedback. So positive feedback, we said, in this context we are talking about oscillators. So positive feedback, we said, we get when if you take a sample from the output and you mix it at the input and add it, not subtract it. If you do that, when you write the transfer function, we said you will get an expression which is a by 1 minus a beta, and we see immediately that if I can satisfy a beta is equal to 1, then the transfer function will have a value infinite, which does not make sense. And we said what it essentially means is that you get an output without giving any input, and that is exactly what is an oscillator. Now we talked about the condition for oscillation. We said that is a beta is equal to 1, which means, because the beta network in this case, unlike the amplifier, is a frequency sensitive circuit or a frequency selective circuit, and we said in an actual oscillator you would actually use a filter, a second order filter or higher order filter. In that case, this condition will be satisfied by satisfying independently two conditions. One is the modulus of a beta must be equal to 1. The other one, the phase of a beta must be equal to 0. And we said what you actually do is to implement, you would choose an amplifier and you would choose a filter, and whatever is the attenuation of the filter will be compensated by the gain of the amplifier, so that your modulus a beta is equal to 1. That is why you would implement. So in a Wein bridge oscillator, which we talked about, we said in a Wein bridge oscillator the gain is chosen as 3 because the attenuation of this particular network is 1/3. So to offset the attenuation, you need to multiply by 3. Now just to give you one quick example, you also have another popular RC oscillator. You also can talk about LC oscillators. LC oscillators are used at RF frequencies, let us say 1 megahertz and high, and these are very difficult to, let us say, analyze and even use them in the lab. And RC is very, very easy to use to understand concepts. So this is something you can easily do, and Wein bridge, I encourage all of you to do it yourself, so that you can teach your students much better, and the conceptual understanding will be much better. Very simple circuit. Now you also have an example of a phase shift oscillator, where you would use a it so happens that you would use a 3 RC network, kind of networks in series there, and the attenuation of that network, if you do the transfer function, you would see that is around 1/29, minus 1/29. Therefore the gain of that amplifier should be minus 29 to get unity. So I think I have come to the end of my lecture.